students, in the last video we studied the exercise example 1.15. In this video we are going to see the exercise example 1.16. See, in this example what is given? The cube is given and the electric field is along the x-axis. We are going to solve this example with the help of exercise example number 15. It is given in the question. Okay. See, so to the phase 1 and to the phase 2, the flux link that we are going to calculate. So flux link with the phase 1, that is phi 1. We can write it is phi 1. So formula for phi electric flux equal to E into A. E is the electric field, A is the air. Right? See, E vector dot A vector means E A cos theta. For the first side, electric field along the, for the first phase, electric field is along the x-axis. So electric field will be like this. Here it is the direction of electric field. It is the direction of area vector. Angle between them is 180 degree. So we will put the value 180 over here. So E A cos 180. As we know that cos 180 equal to minus 1. So we will put the value of cos 180 equal to minus 1. So this phi 1 will become minus of E into A. Right? The next flux link with the second phase that we are going to calculate with the help of formula phi 2 equal to E into A. The same electric field link with the phase 2 in the direction along x-axis. Here it is the E vector. Here it is A vector. E vector and A vector now parallel. So therefore E vector dot A vector. So here we write E A cos theta. Here the value of theta is 0 degree. So put E A cos 0. Cos 0 become 1. So only it is EA. So phi 2 will becomes EA. Now the total flux link with the cube, that is phi equal to phi 1 plus phi 2. So phi equal to phi 1 plus phi 2. As we know that here phi 1 equal to minus of EA minus of EA plus phi 2 equal to EA. Right? So total flux link with the cube is equal to 0. This is your example 1.16. Correct? Now we will see the example number 1.17. See what is given in that. A careful measurement of the electric field at the surface of the black box indicates the net outward flux through the surface of the box is 8.0 10 to the power 3. Dear students, the flux are given and the flux coming out through the box is given. We are going to write the data or which is given in the question. See, first of all we will make the list over here. What is given, that is flux coming out through the box, that is 8.0 10 to the power 3 Newton meter square per coulomb. The question is, what is the net charge inside the box? Question is net charge inside the box. Right? We can consider this is the box. Right? The number of charges are kept and the flux coming out through the box will be equal to this. Correct? Calculate the net charge. Q equal to question mark. Dear students, here the required formula will be phi equal to charge divided by epsilon 0. Right? So Q equal to question mark. So Q equal to flux into epsilon 0. By putting all the value, we can get the answer. Flux equal to 8.0 10 to the power 3. Right? 8.0 10 to the power 3 and epsilon 0 equal to 8.85 10 to the power minus 2. by solving this you will get the answer, and that is near about, that answer is near about 7.08 10 to the power minus 9 coulomb. Correct? This is your answer. The next question B. The second question, second part of the question. If the net outward flux through the surface of the box were 0, right? Could you conclude that there were no charges inside the box? Suppose students, see here it is a box and the flux are not coming to this box. It means the box has no charge. The charges are not enclosed in the box, right? This is the first meaning we can conclude. And second thing we can say that if there are charges, then total charge inside the box will be 0. Suppose there are plus q charge, minus q charge, and total charge becomes 0. In that case only, the flux coming out through the q will be 0. Right? See what we are going to conclude earlier. The first thing, in which cases the flux coming out through the box will be 0. The first case will be if the box has no charge. If there is no charge inside the box, this is the first case. And in the second case, if the box contains charges, but if the total or if the summation of the charges enclosed by the box equal to 0, right? Therefore, the flux coming out through the box will be 0, right? So these are the two cases. This is your example number 1.16. Now we are going to see the next example, that is 1.17. Example number 1.18. See, a point charge 10 coulomb, microcoulomb, is at a distance 5 cm directly above the center of the square of the side 10 cm as shown in the figure. The diagram is given to you, students. What is the magnitude of electric flux to the square? Hint is given. Think of the square as one face of the cube. Think of the square as a one face of the cube with edge of 10 cm. Students, see, suppose here it is a square. Oh, okay, we can consider book as a square. At a 5 cm from the center of the square, this is the square. Suppose this is the center, geometrical center of the square. At a 5 cm perpendicular distance, 5 cm over here, the charge is kept. And in the hint it is given, consider it is a cube. The square number 1, square number 2, square number 3, square number 4, square number 5 and square number 6. If we consider the 6 faces, or we can consider 6 squares, means this charge is now enclosed by the cube. Now the charge is enclosed by the cube. See, this is the cube, right? See, this is the cube. The charge is enclosed by the cube. Here is the charge. How many flux are coming out through the whole cube? That we can calculate. Phi equal to charge divided by epsilon 0. The flux coming out through the whole cube, that is Q equal to, right? So this is the, right? But we want to calculate the flux coming out through any one of the faces. The cube has 6 faces. The cube has 6 faces. If we want to calculate the flux through any surface, means square, any face, suppose this is the face, or we can consider this face also, any one face. The flux coming out through any one of the face, at that time we will divide over here or multiplied over here 1 by 6 q divided by epsilon 0. It is the flux coming through whole q. Now here we are going to calculate the flux through any one of the phase, right? So that's why we will multiply by 1 by 6. Flux through whole surface, flux through any surface, any phase. So you just put the value, that is q equal to 10, it is given, 10 to the power minus 6 microcoulomb is given. Here 6 multiplied by 8.85, 10 to the power minus 12. So this is the flux. By calculating this, you will get the answer, and that is nearly equal to 1.88 10 to the power 5. 1.88 10 to the power 5 vapor. Right? It was your example 1.18. Now we will see the example number 1.19. Example 1.19. See what is given? A point charge 2 microcoulomb, q equal to 2 microcoulomb charge is at the center of the cubic Gaussian surface of a side 9 cm. So first of all we will draw a one cube over here, and this cube has a side of 9 cm, right? This is the 9 cm, it is also 9 cm, and it is also a 9 cm. And charge is kept inside the cube, anywhere. Center of the cubic Gaussian surface. Charge is kept on the center. What is the net electric flux to the surface? It's a very simple question. So flux equal to q divided by epsilon 0. Charge enclosed by the Gaussian surface. Gaussian surface is cube over here, right? So q equal to 2 into 10 to the power minus 6 epsilon 0 8.85 10 to the power minus 12. You just get your answer by calculating this, right? So it's very simple, very easy question. Correct? Next, that is 1.20. This is homework for you. Get the answer. 1.20. See what is given over here. A point charge causes an electric flux. So flux equal to minus of 1.0 10 to the power 3 Newton meter square per coulomb. To pass through the spherical Gaussian surface of a 10 cm radius centered on the charge. Right? See, the spherical surface is given and the radius of the spherical surface is 10 cm. Spherical surface, radius is 10 cm. Radius is 10 cm, and the point charge causes electric flux of a minus 1 10 to the power 3 Newton per pass through the spherical Gaussian surface. So electrical flux coming out through the spherical surface equal to 5 equal to this. The question: if radius of the Gaussian surface were doubled, how much flux would pass through the surface? Right? That is your question. First of all, if the radius of the, suppose flux equal to this much, we can calculate flux equal to q divided by epsilon 0. So q equal to, we can calculate, that is 5 into epsilon 0, right? So by putting the value of 5 epsilon 0, you can calculate charge enclosed by the spherical surface, right? The question is, the flux right now, when the radius is 10 cm, the flux coming out through the surface is 1.0 10 to the power 3. If doubled, means radius becomes 20 centimeter. Radius becomes 20 centimeter. So flux coming out through the spherical surface equal to what? Flux equal to question mark when r equal to 20 centimeter. Dear students, when we studied the characteristics of Gauss law, at that time what we studied, it does not depend. The flux, right? The electric field lines are coming perpendicularly to the surface, and it does not depend on the dimension of the body. If the radius becomes double, the number of flux oriented is minus of 1.10 to the power 3. The same flux will lead to the r equal to 20 centimeter sphere, right? So flux will be the same, right? The flux equal to minus of 1.0 10 to the power 3 Newton meter square per coulomb. The same flux will lead to the r equal to 20 centimeter sphere, correct? And we can calculate number of charge inside this q equal to this. Here the flux r minus, means we can say that negative charge is enclosed by the Gaussian surface, because electric field lines are coming towards, right? That's why we can say negative charge is inside the Gaussian surface. That we can conclude if the flux are negative. This much your answer, example 1.20. Now we will see the example number 1.21. A conducting sphere of radius 10 centimeter, radius r equal to 10 centimeter, has an unknown charge. If the electric field 20 centimeter from the center of the sphere is, so electric field is given, electric field E equal to 1.5 10 to the power 3 Newton per coulomb at a distance 20 centimeter. So distance D equal to 20 10 to the power minus 2 centimeter radially inward, right? What is the net charge on the sphere? So charge on sphere Q equal to question mark. Correct? Students, here the sphere is given to you. The sphere has a radius r equal to 10 centimeter at a distance 20 centimeter, right here 20 centimeter. Electric field is given to you, and what is the electric field over here? That is also given to you. Find the charge on the sphere. What are the charges on the sphere that we are going to calculate? We can consider these charges as a point charge. So using the formula E equal to KQ by R square. Here the distance we can denote by letter D. So we will write KQ by D square. Putting all the value K equal to 9 10 to the power 9, right? Charge we want to calculate. The D is given, that is 20 into 10 to the power minus 2 bracket square, and the value of electric field is given, and that is equal to 1.5 10 to the power 3, right? 9 10 to the power 9, it is a Q divided by, right, 20 into 10 to the power minus 2 bracket square. By solving this, you can calculate your answer, that Q equal to, you just do the calculation at your home, minus 6.67 10 to the power that is equal to minus of 9 coulomb. And students, in the question it is given the fields, electric field lines are radially inverse. Radially, electric field lines are radially inverse, means negative charge are on the surface. So we write Q equal to over minus of 6.67. Why we are writing minus over here? Because in the question it is given the electric line, the points radially inverse. So radially inward for the word radially inward, we are writing the minus over here, right? Okay, in this way we studied up to the example, exercise example 1.21. In the next video we will see the 1.22